Okay, so let's unpack this. We talk constantly about large language models, how fast they are, how smart they sound, but the journey from just this, massive dump of raw web data to a truly helpful aligned assistant is, well, it's one of the most intense engineering feats of our time.
It really is. And I think what's fascinating here is understanding the historical context. If you look back, say, a decade ago, if you wanted a model to detect spam, you trained one model just for spam. For translation, another model. LLMs operate on a completely different paradigm. It's all about transfer learning.
Right, which is this idea that the model first learns the foundational knowledge, the rules of language itself on an impossibly large data set, and only then do you tune that enormous intelligent brain for specific usable tasks.
Exactly. The core intelligence gets transferred.
Yeah.
So our mission for this deep dive is to explore those three main stages. First, the brute force, incredibly expensive pre-training stage. Second, all the sophisticated engineering tricks you need to even manage the hardware. And finally, the crucial fine-tuning that makes it, useful.
Let's start with the foundation then, pre-training. This is the stage that costs tens, sometimes hundreds of millions of dollars. And the goal, at its core, sounds deceptively simple. Predict the next token.
Simple goal, impossible scale. I mean, to do this, you feed it everything. We're talking about massive amounts of data scraped from the public internet. Things like Common Crawl, which is an archive of billions of web pages. You've got huge troves of code from GitHub, from Stack Overflow. It's all just text across every language they can find to teach the model how to build a coherent sequence.
And that scale is really the key concept here. If you want a memorable benchmark for how fast things are escalating, just look at GPT-3. That was trained on roughly 300 billion tokens.
And that number, which sounded huge at the time, is now historically small. Llama 3, which is much more recent, was trained on 15 trillion tokens.
15.
Trillion.
15 trillion. That's a 50x increase. It just shows you how aggressive the scaling demands have become.
So if we're talking about this kind of staggering computation, how do we even quantify it? How do you put a number on the sheer work being done? We use a unit called FLOPs, floating operations. It's a measure of the total number of arithmetic operations performed during training. A modern, state-of-the-art LLM is on the order of 10 to the power of 25 FLOPs.
That number is so large it just loses all meaning. What does that even compare to? Is that more than, say, mining all the Bitcoin that's ever existed?
Oh, significantly more. It's a scale of computation we've, frankly, never seen before in any single human project. The total FLOPs needed is basically a function of the number of tokens multiplied by the number of parameters in the model.
Okay, so FLOPs with an S is the total work, the volume, and then there's FLOPS per second, which is the speed of your hardware.
Correct. That's the speed of your GPU cluster, speed versus volume.
Which brings us to the scaling laws. Around 2020, researchers figured out this key trade-off, right? That performance improves with more compute, more data, and bigger models. But there's an optimal relationship, which is the chinchilla observation.
That was the breakthrough. The finding was that for the best use of your compute, your training dataset should be about 20 times the size of your model's parameters. This just fundamentally changed the game.
So if you look back at something like GPT-3, with 175 billion parameters on only 300 billion tokens, it completely violates that ratio. By that rule, it was severely undertrained.
That's the consequence. By today's standard, GPT-3 left a huge amount of performance on the table. It stopped training too soon for its size. They could have gotten a much better model if they'd just used more data, which is why we've seen token counts explode since then.
That's incredible. If a world-changing model like GPT-3 was considered undertrained,
Yeah,
it just shows how fast this is all moving.
it's a constant race. And quickly, before we move on, we have to mention the two big limitations of pre-training.
The first one being the knowledge cutoff date.
Precisely. The model only knows what happened up until its training data was collected. If it was finalized on September 30th, it has no idea what happened in October. And the second is the constant risk of plagiarism, where it might just spit out text it saw during training verbatim.
Okay, so we've built this massive knowledgeable brain. Now we hit the wall, the engineering challenge of actually training it. You have billions of parameters, all the intermediate data, the activations, the gradients, the optimizer states.
All of this needs memory, and memory is the real bottleneck. Even a cutting-edge GPU like an H100 only has about 80 gigabytes of VRAM. You simply cannot store everything for a trillion-parameter model on a single device. It's impossible.
So the solution is parallelism. You have to distribute the workload. How does that work?
They distribute the load across hundreds, sometimes thousands, of GPUs. The first method is data parallelism, or DP. You just divide the batch of data across all your devices. Each GPU computes its own passes, which reduces the memory load from the batch size.
So they're all working on different pieces. They have to talk to each other, right?
Sure. And that's the Achilles heel. You have to aggregate or average all the gradients to update the weights. That creates this huge, slow communication overhead between the devices.
And to deal with all that redundant data, we get into these more sophisticated techniques like zero redundancy optimization.
Zero is all about minimizing that redundancy by sharding. Instead of every GPU holding a full copy of everything, you divide it all up. 0.1 shards the optimizer states, 0.2 adds the gradients, and 0.3 is the most aggressive. It shards the optimizer states, the gradients, and the model parameters themselves.
Wait, hold on. Sharding the parameters, so you're saying the actual model, the billions of numbers that define it, is literally split into pieces across different GPUs.
That's exactly what it means. And this is crucial because it takes models that were once restricted to only the biggest data centers and makes them trainable on smaller clusters. It sort of democratizes the top end of LLM research, even if it adds a bit more communication cost.
That makes sense. So data parallelism is like giving tasks to multiple workers. But then you also need model parallelism. That's for when a single task is too big for any one worker.
Exactly. Model parallelism is about parallelizing the operations within a single batch. This includes things like tensor parallelism for big matrix multiplications, pipeline parallelism for splitting layers across devices, and expert parallelism for those mixture of expert models. It's a whole menu of options to get around that memory bottleneck.
Okay, so we've solved fitting the model onto the GPUs with parallelism, but that created a new problem. All this communication overhead. So now we have to look inside the chip itself for speed hacks.
And this leads us to one of the biggest breakthroughs, flash attention, from Stanford in 2022. To really get this, you have to understand the two memory types on a GPU. You have the large but slow HBM, that's your main memory, tens of gigabytes, and then you have the tiny but super fast SRAM on the chip itself. It's only tens of megabytes, but it's about 10 times faster.
And the problem with standard self-attention is all the back and forth, right? Too many slow read and write operations between that fast little SRAM and the slow big HBM. The bottleneck isn't the math, it's the data movement.
Precisely. So flash attention uses a mathematical trick called tiling to break the attention calculation into smaller blocks. The genius insight is that you can compute these small blocks completely, end to end, including the softmax, entirely within that fast SRAM. This just minimizes the slow HBM transfers.
And this optimization is so good that it enables another trick, recomputation. Can you walk us through that trade-off?
Sure. Normally, you save all the intermediate activation data during the forward pass to use later for calculating gradients in the backward pass. But if the calculation is now lightning fast because of flash attention, you can just discard the activations and recompute them on the fly during the backward pass instead of storing them.
So you're actually doing more arithmetic, more FLRPs.
Yeah.
You're slashing the slow memory operations that were the real problem.
And the results are just astounding. Published examples show HBM read-write dropping from over 40 gigabytes to under 5. The total runtime can drop by a factor of 5 or 6. It's faster training and huge memory savings. It's the best of both worlds.
It's incredible that this was only published in 2022, and it's already standard practice. Just shows you how fast things change. Alongside that, we have to talk about quantization. The whole idea of, does a weight really need 32 bits of accuracy?
Exactly. If we can reduce the numerical precision from, say, 32-bit floating point FP32 to half precision like FP16 or BF16, we save memory and we speed up computation. A lot of GPUs actually have double the compute speed at lower precision.
You mentioned FP16 and BF16. What's the difference there? Why does that matter?
So FP16 is standard half precision. BF16, or bfloat16, is a special format that sacrifices a bit of decimal accuracy to preserve a much wider range of numbers. This is really important in LLM training because it helps prevent numerical overflow with huge values, which can literally crash the whole training process. The standard today is mixed precision training.
Okay, so what's the mix?
You keep the core model weights themselves in high precision FP32 to stop errors from accumulating over time. But the heavy lifting, the forward and backward passes, you do all that in the faster, lower precision BF16. It's maximum efficiency while keeping just enough precision.
All right, so we've built the brain, we've optimized it, now we have to teach it manners. We're moving from just predicting the next token to acting like a helpful assistant, I'm thinking of our teddy bear washing analogy.
Right. A purely pre-trained model might see the prompt, "Can I put my teddy bear in the washing machine?" and just spit back facts about the material composition of teddy bears. It's not being helpful, it's just complete in text based on what it's seen.
But the aligned model gives you the helpful advice. No, you should hand wash it gently.
That transformation is the job of supervised fine-tuning, or SFT, also called instruction tuning. We train the model on these high-quality pairs of inputs and desired outputs, forcing it to learn that assistant-like behavior.
And what's the key difference in the loss function here compared to pre-training?
In pre-training, the model gets a loss score on every single token it predicts. In SFT, the loss is only applied to the generated output. The user's input is fixed. We don't want the model to predict our question, we want it to answer it.
And the data scale just changes completely here. It's about quality, not quantity.
Absolutely. Trillions of raw tokens for pre-training. For SFT, you use these highly curated data sets. We're talking assistant dialogues, math problems, code examples, and this is critical safety alignment data. Prompts designed to teach the model to reject harmful requests. Llama 3, with its 15 trillion pre-training tokens, only used about 10 million SFT examples.
So how do you even know if these models are any good after SFT? The evaluation seems so messy.
It is complicated. You have quantitative benchmarks like MMLU for general knowledge or human evil for code, but you always have the problem of training on the test. Models can be optimized to ace the benchmark without being genuinely more capable in the real world.
Which is why we have things like the chatbot arena, right? To try and quantify the subjective experience, the vibes.
Exactly. Users submit prompts, get 2 anonymous outputs, and vote on which is better. It's a measure of user preference. But even that is flawed. It's noisy, it's subject to user biases. Maybe you prefer emojis, maybe you don't.
Or you might downvote a model for rejecting a harmful prompt, even though that rejection is exactly what the safety alignment is supposed to do.
That's a perfect example. So SFT is the first step toward alignment, but its success depends entirely on getting this phase right, despite all the flawed metrics.
And speaking of cost, SFT is still expensive, especially if you need lots of specialized models, one for customer service, one for legal review, and so on. We need efficient ways to do this.
This is where LoRA, or low-rank adaptation, comes in. It's just a spectacular efficiency gain that really changes the economics of specialization.
How does it work without retraining that whole colossal model?
LoRA takes the huge pre-trained weight matrix, let's call it W0, and it freezes it completely. Instead of tuning those billions of parameters, it adds 2 tiny trainable matrices whose product approximates the change you would have made to the big matrix. You only train those 2 little ones. The rank, or R, of these matrices is really low, usually under 10.
So instead of tuning billions of parameters, you freeze the bulk and just tune a few million extra parameters that are kind of tacked on the side.
Precisely. You save vast amounts of memory and compute, and current best practice is to apply LoRA not just to the attention matrices, but also to the feed-forward blocks. That's where a lot of the performance gain comes from.
And the ultimate efficiency hack is combining this with quantization. LoRA.
LoRA is the marriage of LoRA and smart quantization. The massive frozen W0 matrix gets aggressively quantized using a clever format like NF4, which is normal for 4-bit.
Yeah.
The genius of NF4 is that it uses the statistical distribution of the weights to allocate its 4 bits most efficiently.
And the small LoRA matrices that are actually being trained, they're kept in higher precision.
Yes. They're learned in BF16, so you get a high-quality update, while the static base model has a tiny memory footprint. The combined result is up to a 16x VRAM saving during fine-tuning. It shows how engineering lets smaller teams specialize these massive models on hardware that would have been impossible before.
So we've gone on this amazing journey, from the brute force need for trillions of tokens and pre-training, through the engineering feats of distributed training and flash attention, all the way to this incredibly efficient specialization with QLR. The core knowledge is built on massive data, but the usability, the accessibility, that relies entirely on these sophisticated engineering tricks.
That is the core takeaway for you. The final helpful product is really a victory of deep optimization. It's about making the impossible scale manageable and specialized.
And that leads us to our final provocative thought for you to mull over. We saw that the alignment state relies heavily on evaluations, whether it's academic benchmarks or user preference scores like Chatbot Arena. If we know that both of these metrics can be flawed or gamed, what happens when the next stage of training, preference tuning, relies on those imperfect signals? Is the optimal model truly defined by its intrinsic knowledge, or is it just defined by a successful strategy for optimizing a flawed evaluation system? Something to think about.